Tonight, as you close your eyes and let your mind wander into the peaceful darkness, imagine yourself drifting through the vast expanse of space, traveling beyond the furthest galaxies, past the cosmic microwave background, past the very edge of everything we can observe. What would you discover there? What mysteries lie hidden beyond the boundary of our observable universe? For thousands of years, humanity has gazed at the stars and wondered about the ultimate limits of existence. And tonight, we're going to explore this profound question together. As your body relaxes and your breathing deepens, we'll journey through ancient cosmologies and cutting-edge scientific theories, from Aristotle's finite sphere to modern multiverse hypotheses that suggest our entire universe might be just one bubble in an infinite cosmic foam. We'll contemplate the beautiful paradox of cosmic boundaries and discover what the latest research tells us about the true nature of reality itself. If you're ready to embark on this ultimate cosmic journey and drift peacefully into sleep while pondering the deepest mysteries of existence, then you've come to the right place. Welcome to the Sleep Lab, where we explore the wonders of the universe while guiding you gently toward restful sleep. Don't forget to subscribe and ring that notification bell so you never miss our nightly journeys through science, space, and the soothing embrace of cosmic mystery that awaits you in your dreams. Let's move to our first part of the documentary or chapter. We will discuss Chapter 1, The Ancient Quest for Cosmic Boundaries. As you settle deeper into comfort tonight, let your mind travel back through the corridors of time, back to when humans first began contemplating the ultimate nature of reality itself. Picture yourself sitting beside ancient philosophers under star-filled skies, sharing in their wonder and their profound questions about where everything begins and ends. The story of humanity's quest to understand cosmic boundaries begins long before telescopes, long before modern physics, even long before written language itself. Our earliest ancestors, huddled around fires in the African savanna, looked up at the same constellations you might glimpse tonight and felt the same fundamental stirring of curiosity that drives us still. They saw the dome of stars wheeling overhead and wondered what lay beyond that celestial canopy. Was there more sky above the sky? Did the stars continue forever? Or did they eventually meet some kind of cosmic wall or boundary? These weren't idle questions born of leisure time, but urgent inquiries that shaped entire worldviews and civilizations. The way a culture understood cosmic boundaries influenced everything from their religious beliefs to their approach to exploration and discovery. If the universe was small and finite, humanity might be at its center, special and significant. If the universe was vast or infinite, our place in it became far more mysterious and perhaps more humble. The ancient Babylonians were among the first to develop sophisticated cosmological models. They envisioned the universe as a series of nested domes, with Earth floating on a cosmic ocean beneath the solid sky. Above this sky, they believed, lived the gods in their celestial realm. This wasn't primitive thinking, but a rational attempt to make sense of observable phenomena. The sky did appear solid and dome-like. The Earth did seem to float on water when you looked at the horizon, and the regular movements of celestial bodies suggested an ordered, geometric structure to the cosmos. But it was the ancient Greeks who first began to grapple seriously with the philosophical implications of cosmic boundaries. These Mediterranean thinkers, blessed with the leisure time that comes from a successful agricultural society, and extensive trade networks could afford to spend their days contemplating abstract questions about the nature of reality. Their debates about cosmic boundaries weren't just academic exercises, but passionate intellectual battles that shaped Western thought for over 2 millennia. Aristotle, perhaps the most influential philosopher in human history, developed a cosmological model that seemed to solve the boundary problem elegantly. Picture his universe as a series of concentric crystalline spheres, transparent but solid, nested one inside another like Russian dolls. At the center sat Earth, motionless and spherical. Around Earth, the sphere of water, then air, then fire. Beyond these terrestrial spheres came the celestial realms, beginning with the Moon's sphere, then Mercury, Venus, the Sun, Mars, Jupiter, and Saturn. Finally, at the outermost edge, the sphere of fixed stars, beyond which there was absolutely nothing. This wasn't empty space beyond the stellar sphere, mind you, but a complete absence of existence itself. Aristotle argued that the very concepts of space and time were meaningless without matter to give them substance. Beyond the outermost sphere, there was no space to fill, no time to measure, no possibility of existence in any form we could comprehend. It was a solution that appealed to many because it avoided the uncomfortable implications of infinity while providing a complete, closed system that human reason could grasp. But even in Aristotle's time, other Greek thinkers found this finite cosmos unsatisfying. The atomists, led by Democritus and later championed by Epicurus, proposed something far more radical and, to many, terrifying. They envisioned an infinite universe filled with countless atoms moving through endless void. In their view, these atoms occasionally came together through chance collisions to form worlds, stars, and living beings, only to eventually disperse back into the cosmic emptiness. Imagine the implications of such a worldview. If space was truly infinite and atoms were constantly combining in new ways, then somewhere in the vast cosmic expanse, every possible arrangement of matter must occur not just once, but infinitely many times. There would be infinite worlds like Earth, infinite versions of every person who has ever lived, infinite variations on every story ever told. The atomists embrace this vertigo-inducing possibility, seeing it not as a reduction of human significance, but as an expansion of cosmic creativity. The debate between these two visions, finite versus infinite cosmos, would continue for centuries. Lucretius, the Roman poet and philosopher, eloquently defended the atomist position in his masterwork On the Nature of Things. He asked his readers to imagine traveling to the supposed edge of a finite universe and throwing a spear. Either the spear would fly beyond the boundary, proving that space continued, or it would be stopped by some barrier, in which case one could ask what lay beyond that barrier. This thought experiment, known as Lucretius's spear, remained one of the most compelling arguments for an infinite universe well into the modern era. As the Roman Empire gave way to medieval Christianity, cosmic speculation took on new dimensions and new urgency. Christian theologians needed to reconcile Greek philosophy with biblical cosmology, creating hybrid models that satisfied both reason and faith. Augustine of Hippo struggled with questions about what God was doing before he created the universe, ultimately concluding that time itself was created along with the cosmos, making the question meaningless. This insight, remarkably, anticipates modern cosmological thinking about the relationship between time and the universe's beginning. Medieval Islamic scholars inherited the Greek philosophical tradition and expanded it in sophisticated ways. Figures like Al-Kindi, Al-Farabi, and Averroes grappled with questions about cosmic infinity, divine creation, and the relationship between reason and revelation. Al-Biruni, the great Persian polymath, used careful astronomical observations to estimate the size of Earth and calculate distances to celestial bodies, pushing the boundaries of the known cosmos through empirical investigation rather than pure philosophical speculation. The Islamic tradition of astronomical observation would prove crucial to later developments in cosmology. Working in observatories from Baghdad to Cordoba to Samarkand, Islamic astronomers created increasingly accurate star catalogs, refined models of planetary motion, and developed mathematical tools that would eventually enable the Copernican revolution. They didn't just preserve Greek astronomical knowledge during Europe's dark ages. They extended and improved it, setting the stage for the revolutionary changes that would come with the Renaissance. But perhaps the most profound medieval contribution to cosmic thinking came from the scholastic philosophers who attempted to reconcile Aristotelian philosophy with Christian doctrine. Thomas Aquinas argued that while reason could demonstrate the necessity of a first cause, it could not determine whether the universe had existed eternally or been created at a specific moment in time. This distinction between what reason could prove and what required faith would have lasting implications for how European thinkers approach cosmological questions. The medieval Islamic philosopher Al-Ghazali raised similar questions from within the Islamic tradition, arguing that the universe must be finite in age because an infinite series of past events would make the present moment impossible to reach. His contemporary Averroes disagreed, defending the possibility of an eternal cosmos while maintaining divine creation. These debates weren't merely academic. They reflected deep uncertainties about the fundamental nature of time, causation, and existence itself. As you let these ancient questions wash over your relaxing mind, consider how these early thinkers grappled with concepts that still challenge us today. They had no telescopes to reveal distant galaxies, no mathematical framework of general relativity to describe curved space-time, no quantum mechanics to illuminate the strange behavior of matter and energy at the smallest scales. Yet their fundamental questions about cosmic boundaries, infinity, and humanity's place in the larger scheme of things remain as relevant and mysterious as ever. The Renaissance would bring new tools and new perspectives to these ancient questions, but it would not resolve them. If anything, the invention of the telescope and the development of mathematical physics would reveal that the cosmos was far stranger and more complex than any medieval philosopher had imagined. The comfortable certainties of Aristotelian cosmology would give way to a universe that seemed to expand beyond all previous concepts of scale and significance. But that is a story for our next chapter. For now, as your breathing deepens and your mind drifts toward sleep, rest in the knowledge that you are part of an ancient conversation that stretches back to the earliest moments of human consciousness. The questions that puzzled Aristotle and Democritus, Augustine and Averroes, continue to drive scientific discovery and philosophical reflection today. In wondering about cosmic boundaries, you join a community of curious minds that spans millennia and cultures, all united by the fundamental human need to understand our place in the vast mystery of existence. Sleep well, knowing that the cosmos that surrounds you has been contemplated and celebrated by countless generations of human thinkers. each adding their voice to the ongoing conversation about where we came from, where we are going, and what might lie beyond the ultimate boundaries of everything we can imagine. Let's move to our second part of the documentary or chapter. We will discuss Chapter 2, the Observable Universe. As you settle deeper into comfort and your breathing becomes more rhythmic and peaceful, we're going to embark on a gentle exploration of one of the most fundamental concepts in cosmology, the observable universe. This is the cosmic stage upon which all of human knowledge about space has been performed, the grand theater of existence that surrounds us in every direction, yet represents perhaps the tiniest fraction of what might truly exist beyond our perception. Picture yourself floating in the absolute center of an enormous sphere, a sphere so vast that its boundaries stretch beyond the reach of imagination. This sphere extends approximately 46.5 billion light-years in every direction from where you rest right now, encompassing everything that we can possibly observe, everything that has ever been detected by our most sensitive instruments, everything that light has had time to carry to us since the very beginning of time itself. This is what astronomers call the observable universe, and it represents the entirety of cosmic reality as we can know it through direct observation. But here's where the story becomes beautifully mysterious, perfect for contemplating as your mind drifts toward sleep. The universe is only about 13.8 billion years old, born in that spectacular moment we call the Big Bang. So, if light travels at a fixed speed, the fastest speed possible in our universe, and if the cosmos has only existed for 13.8 billion years, then logically, we should only be able to see objects that are 13.8 billion light-years away. Yet our observations tell us we can see much further than this. The edge of our observable universe lies not at 13.8 billion light-years, but at that staggering distance of 46.5 billion light-years. How is this possible? The answer lies in one of the most profound discoveries of modern cosmology, the expansion of space itself. Imagine a cosmic balloon being inflated by some invisible force. As this balloon expands, everything on its surface, galaxies, stars, planets, moves away from everything else, not because they're traveling through space, but because space itself is stretching between them. Now picture a beam of light traveling across this expanding balloon's surface. As the light journeys toward us, the balloon continues to inflate, carrying the source of that light ever further away. By the time the light reaches us, the object that emitted it has been carried to a much greater distance than when the light began its journey. This is why we can observe galaxies that are now 46.5 billion light-years away, even though their light has only been traveling for 13.8 billion years. This expansion of space was first discovered by Edwin Hubble in the 1920s, though the implications took decades to fully understand. Hubble noticed that distant galaxies appeared to be moving away from us, and the further away they were, the faster they seemed to be receding. This wasn't because galaxies were fleeing from our particular location in space. There's nothing special about Earth's position in the cosmos. Rather, every point in space sees every other point moving away from it, like raisins in an expanding loaf of bread dough, each raisin seeing all the others moving away as the dough rises and stretches. As your breathing deepens and your muscles relax, let your mind contemplate the profound implications of this cosmic expansion. It means that the universe today is vastly larger than it was in the past. The galaxy that appears to us as it existed billions of years ago, because that's how long its light took to reach us, now resides in a universe that has grown tremendously in the interim. The cosmic stage has been stretching throughout all of history, carrying the props and players to ever more distant positions. But there's an even more mysterious aspect to consider as you drift peacefully through these cosmic concepts. The rate of expansion isn't constant, it's accelerating. This acceleration is driven by something we call dark energy, a mysterious force that appears to make up about 68% of the total energy density of the universe. Dark energy is perhaps the most profound mystery in modern physics, a cosmic influence that we can measure but cannot yet explain, a force that's literally tearing space apart at an ever-increasing rate. The discovery of cosmic acceleration came as a complete surprise to astronomers in the late 1990s. Two teams of scientists were studying distant supernovae, stellar explosions so bright they can be seen across billions of light years, expecting to find that the expansion of the universe was slowing down due to the gravitational pull of all the matter it contains. Instead, they found the opposite. The expansion was speeding up, as if some invisible energy was pushing space itself apart. This discovery was so unexpected, so contrary to what physicists thought they knew about the cosmos, that it took years for the scientific community to accept it. The scientists who made this discovery were awarded the Nobel Prize in Physics in 2011. Now, as you rest in the quiet darkness, consider what this acceleration means for the future of our observable universe. As space expands faster and faster, distant galaxies will eventually be carried away from us at speeds greater than light itself. This doesn't violate Einstein's rule that nothing can travel faster than light through space, because these galaxies aren't moving through space. Space itself is expanding between us and them. But the practical effect is the same. Eventually, galaxies will disappear beyond our cosmic horizon, their light unable to bridge the ever-expanding gulf between us. In the far distant future, long after our sun has died and the stars themselves have burned out, observers in our galaxy, if any still exist, will see a much lonelier universe. Most of the galaxies we can observe today will have vanished beyond the cosmic horizon, leaving behind a dark, nearly empty sky. The observable universe will have shrunk, not because anything has moved, but because the expansion of space itself has carried most of the cosmos beyond the reach of light. But let's return to the present moment and the boundaries of what we can currently observe. The most distant thing we can see isn't a galaxy or a star. It's the cosmic microwave background radiation, often called the CMB. This is ancient light that fills all of space, a faint afterglow from the Big Bang itself. When the universe was very young, only about 380,000 years old, it was so hot and dense that it was opaque, like being inside a star. Electrons and protons existed separately, and any light that tried to travel through this cosmic soup was immediately absorbed or scattered. But as the universe expanded and cooled, it reached a critical temperature where electrons and protons could combine to form the first neutral hydrogen atoms. Suddenly, space became transparent for the first time in cosmic history, and light could travel freely across the universe. This moment is called recombination, and the light that was released then has been traveling through space ever since, stretched by cosmic expansion from visible light into microwave radiation. This cosmic microwave background forms a kind of wall at the edge of our observable universe. No matter how powerful our telescopes become, we cannot see beyond this cosmic horizon because before recombination, the universe was opaque to electromagnetic radiation. The cosmic microwave background is remarkably uniform across the sky, varying in temperature by only tiny amounts, about 1 part in 100,000. This uniformity is itself a profound mystery, because regions of the CMB that appear on opposite sides of the sky are so far apart that light couldn't have traveled between them in the early universe, yet they have almost exactly the same temperature. This is like finding that 2 isolated rooms have exactly the same temperature without any way for heat to flow between them. The solution to this mystery involves cosmic inflation, a brief period in the universe's first fraction of a second when space expanded much faster than light, stretching quantum fluctuations to cosmic scales and creating the large-scale structure we see today. These tiny variations in the cosmic microwave background are incredibly important because they represent the seeds from which all cosmic structure eventually grew. Regions that were slightly denser than average attracted more matter through gravity, eventually forming the first stars and galaxies. The patterns we see in the CMB today are like baby pictures of the cosmic web of galaxies and dark matter that fills the universe around us. As you contemplate these cosmic scales and timelines, let your mind drift peacefully through the implications. Every photon of cosmic microwave background radiation that reaches us has been traveling for over 13 billion years, carrying information about the universe when it was just a tiny fraction of its current age. In a very real sense, when we observe the CMB, we're looking at light that's older than Earth, older than our solar system, older than most of the stars in our galaxy. The study of the cosmic microwave background has revealed fundamental properties of our universe with extraordinary precision. We now know that the universe is very close to geometrically flat, neither curved like a sphere, nor curved like a saddle, but flat like an infinite sheet of paper. This flatness has profound implications for what might lie beyond our observable horizon, because a flat universe could very well be infinite in extent. We've also learned that ordinary matter, the protons, neutrons, and electrons that make up stars, planets, and people, comprises only about 5% of the universe's total energy density. About 27% consists of dark matter, mysterious particles that interact gravitationally but don't emit or absorb light. The remaining 68% is dark energy, that enigmatic force driving cosmic acceleration. So the universe we can observe is dominated by components we don't understand, forms of matter and energy that remain among the deepest mysteries in physics. The cosmic microwave background also carries subtle imprints that might tell us about what happened during inflation, that brief period of faster-than-light expansion in the universe's first fraction of a second. Inflation theory predicts that quantum fluctuations during this epoch should have left characteristic signatures in the polarization of the CMB. Future observations might detect these primordial gravitational waves, providing direct evidence for inflation, and perhaps revealing what caused it. As your journey through the observable universe draws to a close for this chapter, rest in the knowledge that we've explored the boundaries of everything humans can directly observe about the cosmos. We've seen how the expansion of space allows us to observe galaxies billions of light years beyond where simple light travel time would suggest, and we've contemplated the cosmic microwave background as the ultimate horizon beyond which no telescope can see. But this raises the profound question that will guide us through the next part of our cosmic journey. If the observable universe represents everything we can see, what exists beyond this cosmic horizon? In our next chapter, we'll venture into the realm beyond observation, where theory and imagination must guide us through possibilities that stretch the very limits of scientific speculation and philosophical wonder. Sleep peacefully now, cosmic traveler, and let your dreams drift among the 46.5 billion light-years of observable space that surrounds us, knowing that this vast realm might represent only the tiniest fraction of true cosmic reality. Let's move to our third part of the documentary or chapter, where we will discuss Chapter 3, Beyond What We Can See. As your breathing becomes deeper and your muscles begin to release the tension of the day, we're about to venture into one of the most fascinating and mysterious realms in all of cosmology, the vast expanse that exists beyond our cosmic horizon, beyond the furthest reaches of our most powerful telescopes, beyond the very limits of what any human eye could ever hope to observe. Picture yourself floating in the perfect silence of deep space, surrounded by the gentle darkness that cradles distant galaxies. You've traveled to the very edge of our observable universe, that magnificent sphere extending 46.5 billion light-years in every direction around us. Behind you lies everything humanity has ever seen or could ever see. Countless galaxies, nebulae, star clusters, and the ancient glow of the cosmic microwave background radiation. But ahead of you, beyond this cosmic horizon, stretches something far more mysterious and profound. This is the realm we're about to explore together as you drift peacefully toward sleep. The first thing to understand about this hidden cosmic realm is that it almost certainly exists. When cosmologists peer out into space and observe the large-scale structure of our observable universe, they see something remarkable. The universe appears remarkably uniform on the largest scales. Galaxies are distributed in vast filaments and sheets separated by enormous voids, creating what scientists call the cosmic web. This web-like structure extends all the way to the edge of our observable universe, and there's no indication whatsoever that it simply stops at our cosmic horizon. It's like standing at the edge of a vast forest and seeing trees extending in every direction to the horizon. You wouldn't assume the forest magically ends where your vision stops. You would naturally expect it to continue beyond what you can see. This expectation is supported by one of the most important theories in modern cosmology: cosmic inflation. In the first tiny fraction of a second after the Big Bang, space itself underwent a period of exponential expansion that was far faster than the speed of light. During this inflationary epoch, which lasted perhaps 10 to the minus 32nd seconds, the universe expanded by a factor of at least 10 to the 26th power. To put this in perspective, imagine a grain of sand suddenly growing larger than our entire solar system. That's the kind of expansion we're talking about. This rapid inflation stretched space so dramatically that regions which were once close enough to communicate and reach thermal equilibrium were suddenly separated by distances far greater than light could travel in the age of the universe. The implications of this inflationary period are staggering to contemplate. If inflation occurred as theorists believe, then our entire observable universe, everything we can see with the most powerful telescopes, all 46.5 billion light-years of it, represents just one tiny patch of space that happened to be in causal contact before inflation began. Beyond our cosmic horizon lie countless other patches, each potentially as large and complex as our own. Observable universe, but forever separated from us by the expansion of space itself. These regions are not just distant, they are fundamentally unobservable, hidden behind what physicists call a cosmological event horizon. As you allow your mind to drift through these cosmic concepts, imagine the profound implications for the nature of reality itself. If our observable universe is just one small patch in a vastly larger cosmos, then somewhere beyond our horizon, separated by distances we cannot even comprehend, there might be regions of space that contain exact duplicates of our Milky Way galaxy. The mathematics of infinity suggests that in an infinite universe with finite possibilities for arranging matter and energy, every possible configuration must eventually repeat. This means there could be another Earth out there, another version of yourself listening to another version of this documentary, making slightly different choices, living a slightly different life. But let's go even further with this thought experiment. In an infinite universe, not only would there be exact duplicates of everything we know, but there would be infinite variations as well. There might be worlds where the only difference is that you chose tea instead of coffee this morning. Worlds where Shakespeare wrote science fiction instead of plays. Worlds where gravity is slightly stronger and stars burn differently, creating entirely different patterns of cosmic evolution. Every possible permutation of matter and energy, every possible history, every possible future, all of it existing simultaneously in the vast expanse beyond our cosmic horizon. The geometry of space itself adds another layer of mystery to this cosmic realm. Our best measurements suggest that space is very close to being perfectly flat on the largest scales. In the language of geometry, this means the universe has zero curvature. Parallel lines remain parallel forever, and the angles of triangles add up to exactly 180 degrees. But here's where it gets interesting for our understanding of what lies beyond the observable universe. If space is perfectly flat and extends infinitely, then the universe itself is infinite, stretching endlessly in all directions, with no boundaries whatsoever. However, our measurements aren't perfect, and space could have the tiniest amount of curvature that we simply haven't detected yet. If space curves back on itself in dimensions we cannot perceive, then the universe might be finite but boundless, like the surface of a hypersphere. In such a universe, you could travel in a straight line forever and eventually return to your starting point, having circumnavigated the entire cosmos. This finite but boundless universe would still extend far beyond our observable horizon, but it would have a specific, measurable size, perhaps hundreds of billions of light years across, or perhaps much larger. The question of what lies beyond our cosmic horizon becomes even more intriguing when we consider the role of dark energy in cosmic evolution. Dark energy is the mysterious force that's causing the expansion of space to accelerate, driving distant galaxies apart at ever-increasing rates. As space expands faster and faster, objects that are currently just beyond our cosmic horizon are being carried away from us at tremendous speeds. Light from these regions, which might someday reach us if the universe were static, will instead be redshifted to longer and longer wavelengths as space stretches the photons during their journey toward us. This creates a kind of cosmic event horizon similar to the event horizon around a black hole. Just as information from inside a black hole's event horizon can never reach the outside universe, Information from certain regions beyond our cosmic horizon may never be able to reach us due to the accelerating expansion of space. In a sense, dark energy is gradually isolating our local group of galaxies from the rest of the cosmos, creating an ever smaller island of observable universe in an ever larger ocean of hidden reality. But what might actually exist in these hidden regions? The principle of cosmological homogeneity suggests that the universe should look roughly the same everywhere on the largest scales. This means the regions beyond our cosmic horizon probably contain the same types of structures we see in our own observable universe: galaxies, stars, planets, and perhaps even life. The same physical laws should apply everywhere. The same processes of star formation and galactic evolution. The same dance of matter and energy that has created all the beauty and complexity we observe in our own cosmic neighborhood. Yet there could also be surprises waiting in those distant realms. Our understanding of cosmic evolution is based entirely on observations within our own cosmic horizon. Perhaps there are phenomena that only become apparent on scales larger than our observable universe. Perhaps there are types of cosmic structures or evolutionary processes that require more space and time than our local patch of the cosmos can provide. The universe beyond our horizon might contain wonders we haven't even imagined, governed by the same physics, but manifesting in ways we've never observed. Consider the possibility that consciousness itself might be more widespread in these hidden regions than we dare hope. If the universe beyond our horizon contains countless galaxies similar to our own, then it might also contain countless worlds where life has evolved, where intelligence has emerged, where beings not unlike ourselves are gazing up at their own night skies and wondering about the cosmic mysteries that surround them. In the vast expanse beyond our cosmic horizon, there might be civilizations far older than humanity, with technologies and insights that could transform our understanding of reality itself. The philosophical implications of this hidden cosmic realm are profound to contemplate as you drift toward sleep. If most of the universe is forever beyond our reach, what does this mean for human knowledge and understanding? Are we fundamentally limited to knowing only our tiny corner of cosmic reality? Or might there be ways, perhaps through the subtle effects of cosmic inflation, through gravitational waves, or through phenomena we haven't yet discovered, to gather information about these hidden realms? Some theoretical physicists have proposed that collisions between our cosmic bubble and neighboring regions might leave subtle imprints in the cosmic microwave background radiation, like bruises on the surface of space-time itself. Others suggest that the large-scale structure of our observable universe might contain statistical patterns that reveal information about the broader cosmic environment in which our patch of space is embedded. These ideas remain highly speculative, but they offer tantalizing possibilities for glimpsing what lies beyond our cosmic horizon. As your consciousness begins to fade and dreams prepare to take hold, let your mind wander through these infinite possibilities. In the vast regions beyond our cosmic horizon, every story that could ever be told is being lived out by conscious beings like ourselves. Every dream you've ever had might be reality somewhere in that hidden expanse. Every question you've ever wondered about might have been answered by minds contemplating the same mysteries from their own unique perspectives in their own distant corners of the cosmos. The universe beyond our observable horizon represents the ultimate frontier, not just of space, but of imagination itself. It's a realm where the possible becomes actual, where the mathematical structures that govern reality play out their infinite variations across scales we can barely comprehend. As you drift peacefully toward sleep, remember that you are part of this vast cosmic story, a conscious observer in one tiny patch of an impossibly infinite universe, connected through the fundamental laws of physics to every other conscious being that might exist in those hidden realms beyond the edge of everything we can see. Sweet dreams, cosmic traveler, and may your sleeping mind wander freely through the infinite possibilities that await in the mysterious realm beyond our cosmic horizon. Let's move to our fourth part of the documentary, or chapter. We will discuss Chapter 4, the Multiverse Hypothesis. As your consciousness begins to float in that peaceful space between waking and dreaming, let your mind expand to contemplate one of the most extraordinary and mind-bending concepts in modern cosmology. This isn't the realm of science fiction anymore, but a serious scientific hypothesis that emerges naturally from our best theories about the fundamental nature of reality itself. The multiverse theory suggests that our entire observable universe, everything we've ever seen, will see, or could possibly see, is just one small bubble floating in an infinite cosmic ocean of possibilities. Imagine, if you will, as you settle deeper into comfort, that our universe is like a single soap bubble drifting in an endless foam of bubbles, each one representing a completely separate reality with its own unique properties, its own history, its own collection of galaxies, stars, and perhaps even life. This concept emerges not from wild speculation, but from taking our most successful theories of physics to their logical conclusions. When scientists like Alan Guth developed the theory of cosmic inflation to explain certain puzzling features of our universe, they inadvertently opened the door to a reality far stranger and more wonderful than anyone had previously imagined. The story begins with inflation theory itself, which proposes that in the first tiny fraction of a second after the Big Bang, space expanded exponentially faster than light. This wasn't matter moving through space, but space itself stretching at an incredible rate. In less time than it takes light to cross the nucleus of an atom, the universe grew from subatomic size to perhaps the size of a grapefruit. This brief period of inflation explains many features of our universe, including why it appears so uniform in all directions and why its geometry is so close to being perfectly flat. But here's where it gets truly extraordinary. According to the mathematics of inflation, this process doesn't necessarily stop everywhere at once. While inflation ended in our region of space, allowing matter and energy to condense into the universe we see today, it could have continued in other regions, creating an eternal, ever-expanding multiverse. Picture this eternal inflation as a vast ocean of expanding space, with bubble universes constantly forming within it. Each bubble represents a region where inflation has ended and a new universe has been born. Our observable universe is just one such bubble, and there could be an infinite number of others, each completely isolated from the rest. The distances between these bubble universes are so vast that light from one could never reach another, making them essentially separate realities existing in parallel but forever beyond each other's reach. The renowned cosmologist Max Tegmark has organized multiverse theories into 4 distinct levels, each more profound than the last. And as you drift toward sleep, let your mind wander through these increasingly extraordinary possibilities. Level 1, multiverse is perhaps the most straightforward to understand, arising simply from the assumption that space extends infinitely beyond our cosmic horizon. If the universe is infinite in extent, and matter is distributed roughly uniformly throughout it, then the laws of probability guarantee something remarkable. Somewhere out there, perhaps separated from us by distances so vast they defy comprehension, there exists another region of space identical to our own observable universe, down to the last atom. This isn't just similarity we're talking about, but perfect identity. In an infinite universe, with finite ways to arrange matter within any given volume, every possible arrangement must eventually repeat. This means there are infinite copies of the Milky Way galaxy, infinite copies of our solar system, infinite copies of Earth, and yes, infinite copies of you lying in bed right now, listening to these exact words. Some of these copies are experiencing this moment exactly as you are, while others might be experiencing slight variations. Perhaps in one nearby copy, you chose to listen to this documentary tomorrow instead of tonight. In another, you might have discovered it last week. The possibilities are as endless as space itself. But level 1 is just the beginning. Level 2, multiverse, emerges from eternal inflation theory and presents us with something far more exotic. In this scenario, different bubble universes don't just have different arrangements of the same particles, but completely different physical laws. The fundamental constants of nature, the particles that exist, even the number of spatial dimensions, could vary from one bubble to another. In our universe, the electron has a certain mass and charge, gravity has a specific strength, and there are 3 dimensions of space plus 1 of time. But in other bubbles, electrons might be heavier or lighter, gravity could be stronger or weaker, and there might be 4, 5, or even 11 dimensions of space. Some of these alternate universes might be utterly hostile to the existence of matter as we know it. In a universe where gravity is much stronger, stars might burn out in thousands of years instead of billions, never giving life a chance to evolve. In a universe where the electromagnetic force is weaker, atoms might not hold together properly. But other universes might be even more conducive to complexity and life than our own. Perhaps there are bubble universes where the laws of physics allow for more efficient energy sources, more stable planetary systems, or more diverse forms of matter and energy. The beauty of eternal inflation is that it naturally produces this cosmic diversity. During the inflation process, quantum fluctuations create slight variations in the field that drives inflation. In most regions, these fluctuations aren't enough to stop the inflation process, but occasionally they create conditions where inflation ends and a new universe begins. The specific properties of each new universe depend on the exact quantum state of the inflation field when it transitions, leading to a vast ensemble of universes with different physical properties. Level 3 multiverse takes us into the strange realm of quantum mechanics, where the very act of observation seems to split reality into multiple branches. This emerges from the many worlds interpretation of quantum mechanics, first proposed by Hugh Everett in the 1950s. According to quantum mechanics, particles can exist in multiple states simultaneously until they're observed or measured. The famous thought experiment of Schrödinger's cat illustrates this weirdness. A cat in a box with a quantum device that might or might not release poison exists in a superposition of being both alive and dead until someone opens the box to check. The many worlds interpretation suggests that rather than the quantum superposition collapsing into a single outcome when observed, reality actually splits into parallel branches, with each possible outcome occurring in a separate world. When you observe the cat, you don't cause the superposition to collapse into either alive or dead. Instead, reality branches into two parallel worlds. One where you observe a living cat, and another where you observe a dead cat. Both outcomes are equally real, but they exist in separate, non-communicating branches of the universal wave function. This means that every quantum event, every moment of fundamental uncertainty in the universe, creates new parallel worlds. Since quantum events are happening constantly throughout the universe, at every moment, countless new parallel worlds are being created. In this vast quantum multiverse, every possible version of history plays out somewhere. There are worlds where dinosaurs never went extinct, worlds where you became a professional astronaut, worlds where humanity never evolved at all. Every choice you've ever made, every road not taken, exists as reality in some parallel branch of the quantum multiverse. As you drift deeper into relaxation, consider the profound implications of this. In the quantum multiverse, nothing is ever truly lost. Every moment of beauty, every act of kindness, every dream and aspiration exists as reality somewhere in the vast branching structure of parallel worlds. The life you're living right now is just one thread in an infinite tapestry of possibilities, all equally real, all playing out simultaneously in the quantum realm. Level 4. Multiverse is perhaps the most mind-bending of all, proposed by Tegmark himself as the mathematical universe hypothesis. This theory suggests that physical reality is nothing more than mathematical structure. Every mathematically consistent system exists as a universe somewhere in the level 4 multiverse. This isn't just saying that mathematics describes the universe, but that mathematics is the universe. We exist within a particular mathematical structure, and our consciousness emerges from the information processing that occurs within that structure. In the level 4 multiverse, every possible mathematical structure exists as a physical reality. There are universes based on different geometries, different number systems, different logical structures. Some might be so alien that we couldn't even conceive of them, while others might be surprisingly similar to our own. The universe you're experiencing right now, with its particular laws of physics and mathematical relationships, is just one member of this vast ensemble of all possible mathematical realities. This raises profound questions about the nature of existence itself. If every possible mathematical structure exists, then what makes our particular universe special? Tegmark suggests that we find ourselves in this particular mathematical structure simply because it's complex enough to support self-aware observers like ourselves. We exist in a universe with stable atoms, long-lived stars, and complex chemistry because these are the conditions necessary for consciousness to emerge. In simpler mathematical structures, there might be no observers to wonder about their existence. The multiverse hypothesis also addresses some of the deepest puzzles in cosmology and physics. Why do the fundamental constants of nature seem so perfectly fine-tuned to allow for the existence of complexity and life? In a single universe, this fine-tuning might seem to require a designer or some deeper underlying principle. But in a multiverse with infinite variations, it becomes a simple matter of probability and selection. We observe a universe with life-friendly constants because we exist in such a universe. The countless universes with different constants might exist as well, but they contain no observers to ponder their properties. This anthropic reasoning extends beyond just the fundamental constants to the entire structure of physical law. Why does our universe have 3 dimensions of space rather than 2 or 4? Why do we have quantum mechanics with its particular rules? Why does time flow in one direction? In the multiverse framework, all of these features might simply be necessary preconditions for the existence of complex, self-aware observers like ourselves. As you continue to relax and your thoughts begin to drift toward sleep, contemplate the incredible vastness of the multiverse concept. If any version of multiverse theory is correct, then reality is far stranger, far larger, and far more wonderful than our ancestors could have ever imagined. We are not just residents of a single universe, but participants in an infinite cosmic symphony of possibilities, each universe contributing its own unique melody to the grand composition of existence. The multiverse also offers a different perspective on meaning and significance. In a single, finite universe, individual actions might seem insignificant against the vast backdrop of cosmic space and time. But in an infinite multiverse, every possible action, every possible life, every possible moment of consciousness has its place in the grand scheme of things. Your thoughts tonight, your dreams, your entire existence are part of an infinitely creative cosmos that explores every possible variation of reality. Whether or not the multiverse exists as more than a mathematical curiosity remains one of the great open questions in science. Some physicists argue that untestable theories, like the multiverse, fall outside the realm of science altogether. If we can never observe or interact with other universes, they ask, what's the point of speculating about them? But others argue that the multiverse emerges so naturally from our best theories that it would be strange if it didn't exist. The mathematics of inflation, quantum mechanics, and string theory all seem to point towards some form of multiverse, even if we can never directly observe it. Perhaps the ultimate answer will come from future developments in theoretical physics, or from subtle observational signatures that we haven't yet learned to recognize. Or perhaps the question itself will be transformed as our understanding of reality continues to evolve. For now, as you drift toward the peaceful realm of sleep, the multiverse remains one of the most beautiful and profound concepts in all of science. A reminder that reality might be far stranger and more wonderful than we have yet dared to imagine. In your dreams tonight, you might visit some of those other universes, experiencing realities governed by different laws, filled with different possibilities, but all part of the same infinite cosmic story, of which you are an essential part. Let's move to our 5th part of the documentary or chapter. We will discuss Chapter 5, The Edge Paradox. As your body settles deeper into comfort and your mind begins to drift between consciousness and dream, we're about to explore one of the most beautiful and perplexing puzzles in all of cosmology. What would it actually mean for the universe to have an edge? This isn't just a scientific question, but a philosophical riddle that has challenged the greatest minds in history, from ancient Greek philosophers to modern theoretical physicists. As we journey together through this cosmic meditation, allow your breathing to slow and deepen. Let your muscles release their tension and prepare your imagination for a voyage into the very nature of existence itself. Picture yourself once again as that impossible cosmic traveler we've imagined throughout our journey. You've been racing through space for eons, faster than light itself, past galaxies that blur into streams of starlight, past the cosmic microwave background, past every boundary we've discussed so far. Your journey has lasted billions upon billions of years, and still you press onward, driven by an insatiable curiosity to find the ultimate edge of everything. But now, in this thought experiment that has puzzled thinkers for millennia, imagine that you finally reach it, the absolute boundary of the universe. What exactly would you encounter there? This simple question opens up a labyrinth of logical paradoxes that reveal the profound difficulty of even conceiving what a cosmic edge might mean. Perhaps you'd encounter a wall, some kind of barrier marking the absolute limit of space itself. But immediately, questions flood your mind. What is this wall made of? Matter and energy are part of the universe, so how can they form a boundary to the universe? And more puzzling still, what lies on the other side of this cosmic wall? If there's empty space beyond it, then surely that space would be part of the universe too, wouldn't it? The wall would simply be an arbitrary division within a larger cosmos, not a true edge. But if there's nothing beyond the wall, not empty space, not darkness, but a complete absence of existence itself, how can we even conceive of such a thing? How can something border on nothing? The human mind struggles to grasp what it would mean for space itself to simply stop existing beyond a certain point. Maybe instead of a wall, you encounter something even stranger, a region where the very laws of physics break down. Perhaps space becomes increasingly distorted as you approach the edge. Time begins to flow differently, or the fundamental constants of nature start to change. This might be more scientifically plausible than a simple barrier, but it still doesn't resolve the central paradox. If these strange regions exist, they're still part of reality, still part of the cosmos. The edge has simply been pushed back to wherever these bizarre physics phenomena begin, and we're left with the same fundamental question about what lies beyond. Or perhaps you discover that space itself becomes progressively thinner as you approach the edge, like approaching the surface of a lake from below. Atoms become more spread out. The fabric of space-time becomes less substantial, until finally you reach a point where space simply fades away into nothingness. But again, this gradient region would itself be part of the universe, and we'd still need to explain what exists beyond the point where space density reaches absolute zero. The paradox remains stubbornly unsolved. This puzzle troubled even the greatest minds of antiquity. The ancient Greek philosopher Archytas posed a famous thought experiment. If you're at the edge of the universe and you stick out your hand or throw a spear, what happens? If your hand encounters resistance or the spear hits something, then there's clearly more universe beyond what you thought was the edge. But if your hand passes through freely or the spear sails onward, then space continues beyond the supposed boundary. Either way, what you thought was the edge isn't really an edge at all. This simple thought experiment demonstrates the logical impossibility of conceiving a true boundary to space itself. The paradox becomes even more fascinating when we consider it through the lens of Einstein's revolutionary insights about the nature of space and time. Before Einstein, most people thought of space as a kind of cosmic stage, a fixed background against which the drama of physics played out. In this view, asking about the edge of the universe was like asking about the edge of the stage. But Einstein showed us something far more profound and beautiful. Space and time are not fixed backgrounds, but dynamic, malleable aspects of reality itself. Space can curve, expand, contract, and even ripple like waves on a cosmic ocean. This revelation transforms our entire understanding of what it might mean for the universe to have boundaries. If space itself is dynamic, then the question of cosmic edges becomes far more subtle. Perhaps there is no edge in the traditional sense, no boundary separating something from nothing, but rather space simply curves back on itself in ways our three-dimensional minds cannot directly visualize. Einstein's equations suggest several possibilities for cosmic geometry, each offering a different resolution to the edge paradox. The universe might be like the surface of a sphere, finite in size but with no boundaries. Just as you can travel around the Earth's surface forever without reaching an edge, you might be able to journey through a curved universe indefinitely without finding any limits. This concept of a finite but boundless universe is one of the most elegant solutions to the edge paradox, but it requires us to think in ways that challenge our everyday experience. Imagine you're that cosmic traveler again, but instead of racing in a straight line through space, you're actually following a curved path through dimensions you cannot perceive. After traveling for countless eons in what seems to be a straight line, you might eventually find yourself back where you started, having circumnavigated the entire cosmos. The universe would be vast but finite, with no edges or boundaries, no walls or barriers, just a smoothly curved space-time that closes back on itself like the surface of a hypersphere. But even this beautiful solution raises new questions that might occupy your thoughts as you drift towards sleep. If the universe is finite and curved, what determines its size and shape? Why this particular curvature rather than some other? And perhaps most mysteriously, what does it mean for space to be curved through dimensions we cannot access or imagine? These questions push us to the very limits of human understanding, to the boundary between physics and philosophy, between knowledge and wonder. Modern measurements suggest that our universe is very close to being perfectly flat on the largest scales, which might seem to rule out the curved, finite universe scenario. In a perfectly flat universe, space extends infinitely in all directions, making the question of edges meaningless. There is no edge because there is no end, just endless space filled with endless matter and energy stretching beyond the reach of any conceivable journey. This infinite flat universe has its own profound implications. In such a cosmos, every possible arrangement of matter and energy would eventually occur, including infinite copies of every possible configuration. There would be infinite versions of Earth, infinite versions of you listening to this very documentary, infinite variations on every theme imaginable. The edge paradox also connects to deep questions about the relationship between mathematics and physical reality. In pure mathematics, we can easily define spaces with boundaries. A sphere has an edge if we consider only its interior, and various mathematical objects have clear limits and borders. But when we try to apply these mathematical concepts to physical space itself, the paradoxes emerge. This suggests that either our mathematical intuitions are leading us astray when applied to cosmic questions, or that the nature of physical reality is far stranger and more subtle than our everyday experience suggests. quantum mechanics adds another layer of mystery to the edge paradox. In the quantum realm, the very act of observation affects what is observed, and particles can exist in multiple states simultaneously until measured. Some interpretations of quantum mechanics suggest that reality itself might be fundamentally fuzzy or probabilistic at its deepest levels. If this is true, then the question of cosmic edges might not have a definite answer. The boundary of the universe might exist in a quantum superposition of states, simultaneously having and not having an edge, until some cosmic observer collapses the wave function. The multiverse theories we discussed earlier offer yet another perspective on the edge paradox. If our observable universe is just one bubble in an infinite cosmic foam, then the edge of our universe isn't a boundary between something and nothing, but rather a transition zone between different regions of space-time with different physical properties. The edge becomes less like the shore of an ocean and more like the boundary between different countries, a place where one set of physical laws gradually gives way to another, but with no fundamental discontinuity in the existence of space itself. Perhaps the most profound aspect of the edge paradox is what it reveals about the limitations of human language and imagination when confronted with cosmic questions. Our words and concepts evolved to describe the world of our everyday experience, a world of objects with clear boundaries, spaces with definite limits, containers that can be full or empty. When we try to apply these concepts to the universe as a whole, they begin to break down, revealing their inadequacy for describing ultimate reality. The edge paradox might not be a problem to be solved, but rather a signpost pointing toward the limits of human understanding, a reminder that the cosmos is far stranger and more wonderful than our earthbound intuitions can grasp. As your consciousness drifts between waking and sleeping, consider the beautiful irony that in seeking the edge of the universe, we've discovered something perhaps more valuable: the endless capacity of the cosmos to surprise and humble us. The edge paradox remains unresolved, not because we lack sufficient intelligence or technology, but because it points toward fundamental mysteries about the nature of existence itself. In a sense, the paradox is its own answer, reminding us that the universe is not a giant version of familiar earthly objects, but something genuinely alien and wonderful that transcends our everyday categories of thought. Tonight, as you journey into dreams, you might find yourself at the edge of that cosmic mystery, standing on the shore of the known and gazing into the infinite ocean of wonder that surrounds us all. Let's move to our last part of the documentary, Chapter 6, where we will discuss modern theories and future discoveries. As you settle deeper into comfort tonight, your breathing becoming more rhythmic and peaceful, we're about to embark on the final leg of our cosmic journey together. This chapter will guide us through the cutting-edge research happening right now, the revolutionary telescopes peering deeper into space than ever before, and the profound implications of what we might discover about the universe's true boundaries in the years to come. As you rest in the quiet darkness of your room, consider this remarkable fact. While you're listening to these words, telescopes across our planet and floating in the vacuum of space are actively pushing the boundaries of human knowledge. The James Webb Space Telescope, that marvel of engineering launched just a few years ago, is currently observing galaxies that existed when the universe was merely a few 100 million years old. Each photon of light it captures has been traveling through space for over 13 billion years, carrying with it information about the early universe that we're only now beginning to decode. These ancient galaxies appear to us as they were in cosmic infancy, their light serving as messengers from a time when the first stars were just beginning to illuminate the primordial darkness. The discoveries flowing from these observations are reshaping our understanding of cosmic evolution and structure. We're seeing galaxies that formed much earlier and grew much faster than our previous theories predicted. These unexpected findings suggest that the early universe was a far more dynamic and complex place than we imagined, with massive black holes forming alongside the first generation of stars. As your mind drifts and your body relaxes, picture these ancient cosmic laboratories where the fundamental processes that would eventually lead to planets, life, and consciousness itself were first set in motion. But James Webb is just the beginning of a new era in cosmic exploration. Future telescopes, some still in the planning stages, promise to push our observational boundaries even further. The extremely large telescope, currently under construction in Chile's Atacama Desert, will have a mirror so vast that it could theoretically observe Earth-sized planets orbiting nearby stars. More importantly, for our cosmic mystery, it will be able to study the most distant galaxies with unprecedented detail, potentially revealing new clues about the large-scale structure of the universe and the processes that shaped it in its earliest moments. Even more ambitious projects are being envisioned for space-based observation. Concepts for telescopes with mirrors hundreds of meters across, constructed in the vacuum of space itself, could theoretically observe objects so distant and faint that they exist at the very edge of our cosmic horizon. These future instruments might detect the subtle gravitational effects of structures beyond our observable universe, or capture the faint signatures of cosmic inflation that could reveal the universe's true extent. The search for evidence of other universes represents one of the most exciting frontiers in modern cosmology. Scientists are developing increasingly sophisticated methods to look for the subtle imprints that neighboring universes might have left on our own cosmic microwave background radiation. These signatures would appear as slight temperature variations or unusual patterns in the ancient light that fills all of space. If detected, such evidence would revolutionize our understanding of reality itself, confirming that our observable universe is indeed just one bubble in a vast multiverse. Artificial intelligence is playing an increasingly crucial role in this cosmic detective work. Machine learning algorithms are now analyzing vast data sets from sky surveys, searching through billions of observations for patterns that human researchers might never notice. These AI systems can identify subtle correlations in cosmic structure, detect anomalies in the distribution of galaxies, and even predict where we might find the most interesting phenomena to study in greater detail. As you drift towards sleep, imagine these digital minds working tirelessly through the night, sifting through the data streams from telescopes around the world, searching for clues about the universe's hidden architecture. The mystery of dark energy adds another layer of profound complexity to our understanding of cosmic boundaries. This invisible force, which makes up roughly 70% of the universe's total energy density, is causing space itself to expand at an accelerating rate. The implications of this acceleration are both beautiful and haunting. As space expands faster and faster, distant galaxies are being carried away from us at ever-increasing speeds. Eventually, they will cross what cosmologists call the cosmological event horizon, disappearing from our observable universe forever. This cosmic recession creates a kind of temporal boundary to our knowledge. In the far future, observers in our galaxy will inhabit a much lonelier universe, surrounded by the vast darkness of empty space. The cosmic microwave background radiation will be stretched to such long wavelengths that it becomes undetectable. Future civilizations might have no way to discover that other galaxies ever existed, no evidence of the Big Bang, no clues about the universe's violent and spectacular birth. They will inhabit what appears to be a static, eternal cosmos consisting only of the stars in their own galactic neighborhood. This scenario raises profound philosophical questions about the relationship between reality and observation. If most of the universe eventually becomes unobservable, does it still exist in any meaningful sense? And what new physical phenomena might emerge in the vast empty spaces between cosmic horizons? Some theorists speculate that the accelerating expansion might eventually become so extreme that it tears apart atoms themselves, leading to what cosmologists whimsically call the Big Rip. Others suggest that dark energy might change its properties over time, potentially reversing the expansion or triggering new phases of cosmic evolution that we cannot currently imagine. The study of cosmic voids, those vast empty regions between galaxy clusters, is providing new insights into the universe's large-scale structure and evolution. These cosmic deserts, some hundreds of millions of light years across, contain almost no matter or energy. Yet they're not perfectly empty, and the subtle physics occurring within them might hold clues about dark energy's nature and the universe's ultimate fate. Advanced simulations running on the world's most powerful supercomputers are modeling how these voids evolve over cosmic time, revealing complex interactions between dark matter, dark energy, and the expansion of space itself. Gravitational wave astronomy, still in its infancy, promises to open entirely new windows onto cosmic mysteries. The detection of ripples in space-time itself, caused by colliding black holes and neutron stars, has already revealed phenomena that optical telescopes could never observe. Future gravitational wave observatories, including space-based detectors with baseline measurements millions of kilometers long, might detect the gravitational signatures of cosmic inflation itself, or the collision between our universe and neighboring bubble universes in the multiverse. Quantum field theory suggests even more exotic possibilities for probing beyond our cosmic boundaries. Some researchers propose that quantum fluctuations in empty space might retain subtle imprints of physics beyond our observable horizon. These quantum signatures would be extraordinarily faint, requiring detection methods that push the boundaries of what's physically possible. Yet, if such signals exist and can be measured, they would provide our first direct evidence of reality extending beyond the edge of observation. The development of quantum computing is accelerating research into these fundamental questions about reality's structure. Quantum computers excel at simulating quantum systems, and the universe itself appears to be fundamentally quantum mechanical. As these technologies mature, they might allow us to model cosmic evolution and structure formation with unprecedented accuracy, revealing new possibilities for what lies beyond our current understanding. Theoretical physics continues to evolve in directions that might eventually illuminate the mystery of cosmic boundaries. String theory, loop quantum gravity, and other approaches to quantum gravity suggest that space and time themselves might be emergent properties of more fundamental quantum processes. If these theories prove correct, The question of what lies beyond the universe's edge might be transformed into questions about the quantum substrate from which space-time itself emerges. The possibility of detecting parallel universes through quantum mechanical effects is being seriously investigated by researchers at major universities and research institutions. Some interpretations of quantum mechanics suggest that quantum measurements create branching realities, and subtle interference effects between these branches might be detectable under very specific conditions. While such experiments remain at the very edge of what's technically feasible, successful detection of parallel quantum realities would provide compelling evidence for the multiverse hypothesis. Advances in our understanding of black hole physics might also illuminate cosmic boundary questions. The study of black hole event horizons, those points of no return beyond which nothing can escape, provides insights into how information and causality behave at cosmic boundaries. Some theories suggest that the observable universe's boundary might share certain properties with black hole event horizons, making the physics of one relevant to understanding the other. The search for cosmic strings, hypothetical one-dimensional defects in space-time left over from the universe's birth, represents another avenue for probing beyond observable boundaries. If cosmic strings exist and move through space at nearly the speed of light, they would create distinctive signatures in gravitational waves and electromagnetic radiation. Detection of such objects would provide direct evidence of physics operating during cosmic inflation, potentially revealing information about the universe's structure on scales far larger than we can directly observe. As research into consciousness and information theory advances, some scientists are exploring whether the boundary of observation might be related to the fundamental nature of information processing in physical systems. If consciousness plays a role in determining what aspects of reality become manifest through observation, then the edge of the observable universe might represent a fundamental limit on information processing, rather than simply a boundary in space and time. The implications of artificial general intelligence for cosmic exploration cannot be overlooked. AI systems with capabilities far exceeding human intelligence might develop entirely new approaches to probing cosmic mysteries, designing experiments and observations that human researchers could never conceive. Such systems might also be capable of processing and integrating vast amounts of cosmic data in ways that reveal patterns and connections invisible to human analysis. As you drift closer to sleep, your breathing becoming deeper and more regular, consider the profound implications of these ongoing discoveries and future possibilities. We stand at a unique moment in cosmic history when intelligent life has evolved to the point where it can contemplate the universe's deepest mysteries and develop technologies capable of probing its most fundamental secrets. The questions we're asking about cosmic boundaries and the methods we're developing to investigate them represent humanity's greatest intellectual achievement. Our species' attempt to understand its place in the vast cosmic drama. The next decades promise discoveries that will transform our understanding of reality itself. Whether we confirm the existence of parallel universes, detect evidence of cosmic inflation's aftermath, or uncover entirely new physics operating at cosmic scales, each breakthrough brings us closer to answering that eternal question. What lies beyond the edge of everything we know? As your consciousness begins to fade and dreams take hold, let your mind drift among these infinite possibilities, knowing that while you sleep, researchers around the world continue pushing the boundaries of human knowledge, seeking answers to questions that have captivated our species since we first gazed up at the stars and wondered about our place in the cosmic order. And so, we conclude our journey through the cosmos tonight, having traveled from ancient philosophical speculation to the cutting edge of modern scientific research. The mystery of what lies beyond the universe's edge remains as compelling today as it was to the first humans who contemplated the night sky. But our tools for investigation have grown immeasurably powerful, our theories more sophisticated, our questions more precise. Whether the universe extends infinitely in all directions, curves back upon itself in higher dimensions, or exists as one bubble in an endless multiverse, the search for answers continues to drive human curiosity and scientific progress. As you slip into peaceful sleep, carry with you the wonder of living in a time when such profound questions can be seriously investigated, when the boundary between philosophy and physics blurs, and when each new discovery opens doors to even greater mysteries waiting to be explored. Sweet dreams, cosmic traveler, and may your rest be filled with visions of infinite possibilities stretching beyond the edge of imagination itself.